we talked about Robert Boyle. He was one French chemist. Now we're going to be talking about, I'm going to make sure I get this right, Joseph Louis Gay-Lussac. Long name. Another French chemist who was responsible, rather than Robert Boyle, who was responsible for the relationship between pressure and volume, Gay-Lussac was more interested in pressure and temperature. Okay, so he set out to investigate the effect that temperature, manipulating the temperature at constant volume, okay, very important, has on the pressure of a gas. And what he found was that the relationship between the two is directly proportionate. So as I increase the temperature of a gas at a constant volume, its pressure increases proportionately. Okay. What's important to note is, as well as this being at a constant volume, the temperature scale has to also be in degrees Kelvin, not degrees Celsius. Okay. The reason for that I will explain in this tutorial video, and we'll also talk about Gay-Lussac's equation. Check it out.
Okay, so let's discuss our knowledge of pressure-temperature law to figure out this question. So the question is, find the temperature T2 in degrees Celsius, assuming initial pressure is 20 pascals and initial temperature is 5 Kelvin. Assume the new pressure is 45 pascals. Okay, great. Right, well, we know that we need our temperature to be in Kelvin. Okay, it's asking us to find our new temperature in degrees Celsius. We'll get to that later. But the reason that things need to be in Kelvin is because we know that the Kelvin temperature of a gas is proportional to the average kinetic energy of its molecules, right? We know that as we increase temperature, we give those particles more kinetic energy to move around. And obviously that's related to pressure, right? You think more movement, more collisions, or more frequent collisions, and more collisions means there's more force exerted. And because pressure is equal to force divided by area, we can successfully say that as temperature goes up, pressure goes up, okay? So this sort of gives rise to our equation, right? Where there is a directly proportionate relationship between pressure and temperature, okay? And the reason that it has to be in Kelvin is, I suppose, best explained by a graph that looks a bit like this, where we have pressure here on the y-axis, and then we have temperature in degrees Celsius on the x-axis. And what it actually looks like is this, right? Where pressure is 0 is minus 273 degrees Celsius, okay? And that is 0 Kelvin, okay? So we say that at 0 Kelvin, there is no pressure, okay? Which is why it's so important that we are actually doing everything in Kelvin. So let's look at this question. How do we tackle this? Well, we want to find T2, and we have P1, which is 20, and we have initial temperature, which is 5 Kelvin, and that is equal to 45 divided by x, okay? So we can say that 4 is equal to, because 20 divided by 5 is 4, or we can say, 45 over x, multiply it across by x, and 4x is equal to 45, yeah? Which means x is equal to 45 divided by 4. Okay, and if we put that into our calculator, we know that it is 11.25 Kelvin, but the question wants us to answer our temperature in degrees Celsius, right? So we have to do a bit of converting, and if we know that minus 273 degrees C is equal to 0 Kelvin, we have to add 273 to go from Kelvin. To go from Celsius to Kelvin, we have to add 273, but we're trying to go from Kelvin to Celsius, right? We're trying to go this way, so we have to take away 273, right? And that means that we would end up with minus 261.75 degrees Celsius. And that is our answer.
Okay, so hopefully that helped you understand the equation and the relationship between pressure and temperature in terms of degrees Kelvin. Please check out our previous video on Boyle's law if you haven't already, which will help you understand the relationship between pressure and volume, and then you can put it all together and you'll have a nice comprehensive understanding of pressure, volume and temperature. Please check out our other videos for more really fun physics stuff, and like and subscribe, it really helps us grow the channel. But in the meantime, stay quantum, and I'll see you next time. Bye guys.